Last time we started 1.4, and we had gotten barely to this idea of continuity, this definition, and this is where we ended. And I left this picture. This is a picture I actually drew in my other class on here for a reason. So just to remind you where we were, this continuity definition says that in order for something to be continuous, we actually have to have the limit at the function equal to the function value at the function. And this is actually a picture where you can see that we've got a limit, because this, if we're approaching this open circle from the left or from the right, we're approaching both places, same spot, right? Open circle. But we've got a problem because although the circle's open and the limit exists, the function value is way up here. It's not actually attached to this same spot, right? So this is something that we would call discontinuous. Both the function value exists and the limit exists, but they're not equal to one another. All right, so we're going to do some examples to decide determining whether functions are continuous, if so, where they're continuous. And then we're going to do something called extending our function to a larger domain. So as we're taking a look at this one first, we're supposed to decide where it's continuous. So where are the locations that we've talked about having problems with continuity? How do we find those places? Okay, let me take a step back and ask the question a little bit differently because I don't think I asked it very well. So one way to find where a function is continuous is to decide where it's not continuous. Not continuous is an easier thing to identify than it is to identify where it's continuous. So for a function to be not continuous in a picture sort of view, what did we see happen in our last sections where we had problems with continuity? We didn't call it that. Your asymptotes is one, very good. What else did we see? Holes in the graph, and there's one other thing we could have seen. A jump. Now, in an equation point of view, we're probably not going to see any jumps, but we are going to see asymptotes and holes. So with an equation like this, how do we get an asymptote or a hole to occur? What has to happen?
The hole you can factor out.
Okay.
If you factor something out, then it's a hole, but if you can't, it's x plus 1 is.
Right, that's all good. How do I do it from here, though? Like, you want me to factor, but why do I need to factor this? There's a reason why I need to factor.
To see if it's removable.
You can't divide by 0.
Okay, there's an issue about this division by 0 problem, right? So whether this graph actually has an asymptote or a hole, it has a problem anyway if the denominator is equal to 0, right? That's not good. If the denominator is equal to 0, we've got a problem spot. Now, in a rational function, it means we've either got a hole or an asymptote. So my issue with the continuity is going to be all surrounding this issue of the denominator equaling 0. So when would this denominator equal 0? When x is equal to negative 1. Right, good. All right, so we are discontinuous at x equal negative 1. Now, we don't know how we're discontinuous. That's really not the point because they didn't ask me that. We do know, though, that it's either an asymptote or a hole, right? It's one of the two, because if I let x equal to negative 1, that denominator is going to be 0. So I cannot plug in the number negative 1 because I've either got an asymptote or a hole. So if it's discontinuous at x equals negative 1, we would say that it's continuous, well, everywhere else, because I can plug in any other number I'd like, right? And there's no problems. So the way that I write, I did not spell continuous right. Let's try that again. Continuous. This is continuous from negative infinity to negative 1, union from negative 1 to infinity. This is interval notation. We always are, when we're talking about the real number system, we're always going to start at negative 1 with a parenthesis. In this case, we have this open parenthesis around that negative 1 because we can't actually equal negative 1. That's the point we're excluding. Union means we get to include both pieces of this. Any of the answers along here are valid places where my function is continuous. Okay, so this is half of what we're supposed to do. We're supposed to determine where the function's continuous, and we did that, right? It's continuous from negative infinity to negative 1, and then negative 1 to infinity. Now it says, if possible, extend to a new function that is continuous in a larger domain. So let's first of all address the if possible. This if possible issue surrounds exactly what Zach was saying. Zach, when you looked at this, you talked about wanting to be able to factor something, right?
Yeah.
Now, if you were able to factor this and cancel something out, then you're going to be able to do the rest of the problem. Okay? So if you encounter one in your homework where there's no factoring possible, then it's not possible to extend this. Okay, so jot that down for yourself. Because I'm not going to do an example of one of those, but I do want you to recognize that if that happens, if you can't do any sort of factoring and reducing, then you're not going to be able to extend it. Now, if you can factor and reduce, you might be able to get rid of one of those places if it's a hole in the graph. So that's what we're going to head into next. We're going to take a look at what happens if I try to factor and reduce this. So how will that numerator factor?
X plus 1 is minus 1.
Excellent. So what reduces? The x plus 1. So this function is actually equivalent to the function x minus 1, isn't it? And it's equivalent to x minus 1 everywhere except at x equals negative 1. What happens at x equals negative 1? There's a hole. This same discontinuity spot now that we didn't know whether it was a hole or an asymptote, now we know it's a hole. And it's a hole because I was able to remove the factor that was causing that denominator to be 0. We actually call that a removable discontinuity. And I can't remember if it's in this lesson or the next one, but I'll define that specifically at some point here. It's a removable discontinuity. I can remove it. I can take it away. And we can take it away by doing exactly what I'm about to do here. We're going to extend this function. So this function, new function, is going to be called g of x. You can call it whatever you want. So, maybe you want to use j of x because your name's Jalissa, right? You could do that. I had a student who did that once. She always used the names of her friends for her function names. I know. So what we're going to do is we're going to actually write in the first original function first. Because I want my new function, this g of x function, to be pretty much the same function. That's my goal. I pretty much want it to be the same function I had before. And I'm able to do that, and it will be that first function everywhere when x is not 1, negative 1, excuse me. Because we just sort of decided we can't have x equal to negative 1. It doesn't work. Now I want you to think about this function right here where we simplified. We said that there's a hole in the graph. The hole is at x equals negative 1 because of this right here, right? What does y equal at that point? Negative 2. How'd you get negative 2, Zach? Into what? Into this red one, right? All right, so this is what it reduces to. So there's a hole in the graph when x is equal to negative 1. The corresponding y value is going to be what this would have reduced to, where that hole is missing from that line. And so if I put in negative 1 here, I get negative 2. So the hole in the graph is actually at negative 1, negative 2. So what we want is we want to say that when x is equal to negative 1, then I'm going to fill in the hole. I'm going to actually fill it in. So visibly what we're doing is we originally started with this, and then this piece of this down here allows me to fill in my hole. And that's why it's called a removable discontinuity, because I can fill in the piece that's missing. Now this is extended. I actually can use any x value now at all. I just have to decide what the x value is. If the x value is anything except for negative 1, I'll plug it into the first function. If anything that is actually equal to negative 1, then I know that the answer is negative 2. I've extended this to be valid on the whole domain. So this is actually now continuous. On negative infinity to infinity. It's continuous everywhere now because we redefined that one spot where it had problems. Does it make sense to everybody? Okay, we're going to do another one that looks almost like this one. What's the directions the same? What's the difference in this problem than the one we just did before? Yeah, actually we really just flipped the fraction, didn't we? So we actually have the squared on the bottom, which means that we might have more than one place where it's discontinuous. And we actually do. Where is this function discontinuous? Yeah. It's continuous at discontinuous at x equals negative 1 and x equals positive 1. There's two places, because either of those values make the denominator 0. So when we write the continuous statement, it's a little bit longer to write because I have to say that I can go from negative infinity to negative 1, union from negative 1 to 1, union, and I'm running out of space, but this should go next to this really. It would say 1 to infinity after that last union. So I exclude the negative 1 and the 1. This is how I'd write an interval notation. If interval notation is something that's a little bit fuzzy in your mind, just come ask me some questions about it after class or in my office or something. We can chat about interval notation a little bit. However, so that answers the first question. Let me start there. Where is it continuous? It's continuous on this domain over here that we wrote down. It says, if possible, extend it to a new function. Okay? So again, the if possible, extend it to a new function. When will we be able to do that? If I can factor it. Now, it doesn't have to immediately, I don't have to be able to sort of get rid of the denominator in my factoring. I just have to be able to factor it. And I can factor this and reduce. I should say that too. Factor and reduce in some way. This can factor and reduce. We have factored this already. So we'll just do it again here. And when one factors that, we reduce the same thing we did a minute ago. Except that what does my function end up being in this point here? Right, it's 1 over x minus 1. Yeah, sorry. So I still have a denominator. I still have something that x can't be, right? X can't be what? Still can't be positive 1, right? Even with this new simplified version, I can't plug in the number 1. But in this version, could I now plug in the number negative 1? Yes, I could, which means we've extended, or we've got the ability to extend the graph. So we'll call our new function k of x for fun. We write in the first function that we were given, x plus 1 over x squared minus 1, and we identify that we're not allowed to use that function to plug in the number negative 1 or the number positive 1, right? Now we know, even when we use this reduced version, I can't plug in the number positive 1. But what would happen if I were to plug in the number negative 1 there? I'd get negative 1/2. So the other piece that extends this is to be able to have a place to plug in negative 1/2, or negative 1 into to give me that negative 1/2. So this is not continuous everywhere now, but it is continuous on more of the graph than it was before. Now this is continuous on negative infinity to 1 and 1 to infinity. In other words, I don't have to exclude the negative 1 value because I've identified what it's going to be when it's negative 1. Does that make sense? So you may or may not actually be able to extend this to the whole number line, to negative infinity to infinity. But on this particular one, we were at least able to do it on a larger domain, which is actually what the directions are specifying. It is a larger domain than we had before. All right, this idea of continuity, and you're welcome to flip the page. I'm going to show you back on this one here. It said that if we have a function, it's an open interval containing x equals a. F is continuous at a if the limit equals the function value. Now, it looks like there's just one thing that says, but it actually can be broken down into 3 pieces, which is a lot easier to think about it sometimes, is to think about it as this remark. In order for f to be continuous at x equals a, you actually have to have 3 things happen. The first thing you have to have happen is that the function value has to exist. Okay? I have to be able to plug in 3. If I can't plug in 3 into the function, then it's not going to be continuous. So on this one over here, the function as a whole is not continuous at x equals 1. Because even when I reduced it and created this new k of x, I still can't plug in x equal 1. Okay? The other thing that has to happen is that your limit has to exist. So visually, the kinds of things that we are still not allowing. So visually, for a limit to exist, it has to approach the same value, right? So we can't have any of these jumps in the graph where things don't meet. We can't have asymptotes where one shoots up and the other one shoots down. We can't have any of that or the limit doesn't exist. And the third thing is that while we have to have this defined and the limit must exist, they also must be at the same value. So we can't have that picture that we sort of started out our lesson today with where I had this going on, right? The function value is the solid dot, the limit is down at the open dot, they don't match. So I can't have that going on either. So those are the three things that we have to satisfy in order for something to be continuous at a point A. So we're going to take a function now, and we're going to explain why this function fails to be continuous at the given x value. And we're going to do that by indicating which of the three conditions in definition 4.1 are not met. So here's what I've done. Your directions, when possible, I try to make my directions say exactly what yours will in the book so that you've got a very, very clean parallel to what's going on. Your directions in your book say that you're going to be referring to definition 4.1, but the 3 points are specifically outlined in remark 4.1. Okay, so that's why I put the remark in parentheses, is because that's what we're actually going to be using when we look at our 3 different points. So we're looking at this remark 4.1 to decide which conditions are not met. All right, so the first condition we have to check is the function defined? That is, can I plug in the number 1 into my function? No, this doesn't work, right? Because it gives me a 0 in the denominator. So is my function defined? No, which means that this right here is a problem. We fail to meet the first condition. Second condition, so this is condition I. We'll do this double I. Second condition is the issue of, does the limit exist? Okay, so if we look at the graph, we might be able to make that decision. If we look at a numerical interpretation, we might be able to make the decision. Or if we talk about what we know about this graph, we might be able to make this decision. This graph, what's going to be happening at x equal 1 on this graph? There's only 2 options. The options are whole or asymptote. Which one is it on this one? It's a vertical asymptote. And we're going to talk more about the vertical part of what you just said in the next lesson. It's an asymptote there, right? Because when is it that we get a whole? When we can factor and reduce. And there's no factoring and reducing with x over 1 minus x, right? So this is an asymptote. And if it got an asymptote there, what do you know about limits? They don't exist. And in fact, this is a rough sketch of what this equals, because I'm not going to make sure that I've actually got the value happening, but it's supposed to be doing it at 1. So it looks something like this. One piece is going up and one piece is going down. Don't judge my artwork, I'm not a good artist. But this piece right here is going to infinity and this piece is going to negative infinity, right? So the limit on this one, as x approaches 1 of the function, also does not exist. Now let me make a comment about this. Some of you are using this limit notation and not writing in a function next to it. Okay? You have to talk about the limit of something. It would be kind of equivalent to you saying square root equals 2. Square root doesn't equal anything, right? Square root of 4 would equal 2. So be careful when you're using that limit that you've got to actually caught the limit of something, just like if you were using a square root, the square root of what, in order for that to make sense. All right, so this one right here fails as well. Okay, so what can you tell me then about 3? It doesn't even make sense to talk about 3, does it? Number 3 is a comparison that says that the limit value has to equal the function value. The limit value doesn't exist. The function value doesn't exist. So we can't even talk about them being equal in a way that makes any sense, right? So we can almost say something like that this is not applicable. And it's not applicable because the first 2 items above don't even work. ABLE? Does that look okay? I'm not sure that's spelled right. We'll pretend. All right. So where does this fail? It says, explain why each function fails to be continuous by indicating which 3 conditions it fails. So this fails actually all the conditions. When you see the word explain, it means you're going to write something in real English, okay? I understand that the math that I just wrote makes sense, but it makes sense because I was talking to you while I wrote it, right? So I expect you to have some sort of a writing if it talks about this. This fails all conditions because the function value and limit value do not exist. All right, a couple theorems for us to take a look at. Theorem 4.1 says that there are some functions we have that are just flat out continuous everywhere. One of those functions is polynomials. And the reason that polynomials are continuous everywhere is they don't have any of those denominators to cause any of these problems, right? We talked about polynomials last time. And then also sine and cosine are continuous everywhere. Again, same reason, just like we worked on last time. And then there's this additional nth root business. And it's continuous everywhere as well, as long as you look at some conditions about what's going on. So we talked about this nth root last time before when we were looking at where these continuities would happen, but we were looking at it from a limit perspective instead of a continuity perspective. When n is odd, this would mean you have an odd root, like a cube root, a fifth root. When you have a cube root, a fifth root, any other odd root, you can take that root of any number, positive or negative. For example, if I had the cube root of negative 27, that's perfectly fine. The answer is negative 3, because negative 3 times negative 3 times negative 3 is negative 27. However, that when you have n being even right here, you can't take the even root of something. We talked about this before too. So we've got this additional condition right here that we can only talk about this being continuous on positive x values. Does that make sense? Again, because we can't take the positive, like a square root of negative 27 in the real number systems. This does not exist in the real number system. Okay. Theorem 4.2 says that f and g are continuous at x equals a, then all of the following are true. F plus or minus g is continuous, f times g is continuous, and f divided by g is continuous. And again, we see this looks like that theorem that we had a couple days ago, at least a little bit. And again, we've got this sort of condition down here at the end that if we're looking at this division, we still can't have the value on the bottom being 0 itself. Did everybody get that one written down? Okay. We're all good? All right. All right, Theorem 4.3 says that if we have a limit and it equals L, and f is continuous at L, then we could do a composition of limits. That is, let's say, for instance, that you had the square root of the sine of x. Let's just say that that's what you had. Well, sine of x, that over here in the previous slide, says it's continuous everywhere. Yay, it's continuous everywhere. It's got a limit. We can go with that, right? So that's sine of x. So if we can have any input value there, then we can continue this process, because now we can take the square root of that and do the same thing. So we can do a function inside of a function, and that's what you see have going on here. So if we have a function inside of a function like this, we can take the limit of the inside function. And I've got a typo there, I'm sorry. This should say g of x. You can have a function of the inside function, and then you can take the limit on the outside. And the corollary goes right along with it. It says that if it's continuous at a, then at g of a, then the composition is continuous at a. It's another way of stating the theorem above, just a slightly different version of it. All right, our last piece that we're going to write in this section, I think, or at least on this page, is about interval continuity. So everything we defined before was talking about the continuity of a specific point. Now we're talking about the continuity on an interval of points. So f is continuous. If f is continuous at every point in the interval, then it's continuous on the open interval. Similarly, if it's also continuous at the end points, then it's continuous on the closed interval. So you see those brackets on there. Finally, if it's continuous on negative infinity to infinity, we actually just say that f is continuous. So if you don't see an interval specified, then it's understood to mean everything. It's continuous everywhere. And we were using that already when we defined where it was continuous back in the first couple of examples, right? We even created these intervals, and they were, in fact, open intervals. And on one of them, we actually were able to say that it's continuous everywhere, negative infinity to infinity. So we've already used this sort of an idea in the previous two problems that we looked at. All right, let's take a look at another one that's the same kind of a description. This is determine the intervals on which f is continuous. So you know something about these functions. In fact, you've seen both of these functions used for a really long time now. You know the function 1 over x, and you know the function cosine of stuff. All right, so what's some problems you see with this one? Where are we going to, again, it's easiest to determine where this is continuous by deciding where it's not. Where is this function not going to be continuous? At 0. How come? Right. So the issue is actually because it's in the denominator of the 1 over x portion, right? So there's two parts to this problem. There's the 1 over x part, and then there's the cosine part. The cosine part in this problem doesn't cause any problems, right? Because the cosine of any kind of the cosine exists everywhere. The limit for cosine exists everywhere. But the problem is that the input inside of this cosine function doesn't actually have an x value everywhere. The problem is occurring at x equals to 0. So this function will be continuous from negative infinity to 0 and 0 to infinity. And again, the issue is because the 0 would make this denominator of the 1 over x 0. Any questions on that one? Okay. This is a little bit different. I bring this up, I guess partly I wanted to use this example. Your book gave it as an example, but I also wanted to use it because we're in the middle of tax season. And these are actually one of the kind of things that you see in tax tables. Determine the constant c that makes the function continuous for all x. Give a rationale for why such a function should be continuous. The problem reads the following. Suppose that a state's income tax code states that the tax liability on x dollars of taxable income is given by this piecewise function. So how many of you heard that before in your life something like when people say they crossed into another tax bracket? Have you heard that phrase before? And it usually means that they're now being charged at a higher tax rate than they were before. Okay, that's what they mean by that. There's a misnomer that when people talk about that all of a sudden it means that their income is actually taxed at a higher rate. So like they could make more money and in effect pay more taxes so that their amount that they actually take home was less than before. Have you guys heard people talk about that like in that way before? I hear that frequently. This idea, let's say that, let's just make up a number. They use the number 10,000 here. So let me just use 10,000 as an example. So for instance, somehow that if I'm under 10,000, I owe less amount in taxes. So maybe I take home 8,000 in my actual take-home pay. But if I somehow all of a sudden crossed over and made $10,001, I would actually end up only taking home 7,000 in take-home pay. This is the misconception people have about the tax tables. They don't work like that. They work like this problem is showing. There is a continuity that's going on here. Because you shouldn't, right? You shouldn't be able to make $1 more and actually take less money home. That shouldn't happen. That doesn't make any sense to us. And it really doesn't happen. So let's take a look here. One of the questions it says is give a rationale for the function to be continuous. This should be continuous, right? Because it should be that if I make a little bit more, even if my tax rate's higher, I still don't end up taking home less money. I should pay more in taxes potentially, but it shouldn't affect the fact that I still have more money as well to take home. So if I made $11,000 and I pay some of it in taxes, I should still make more than the $8,000 that I was taking home when I made $10,000, right? I should still also have more take-home pay. So this is the rationale kind of thing. So go ahead and jot something down about that so that you have it written down. I don't have enough space to write, so I'm going to let you write yours on your paper. So the rationale issue has to do with the fact that in order for this to make sense, when I make more money, I should also take home more money, right? I shouldn't have this discontinuity in these taxes. There shouldn't be this vast amount of a jump in my taxes so that I actually end up taking home less money than I made when I made a lesser income. right, now we're going to determine what the value for C is. In order for this to be continuous, what has to happen is that these two pieces of the graph right here and here have to have the same limit. They have to approach the same limit value. That is, the limit of my function t of x as x approaches $10,000 from the right has to equal the limit of t of x as x approaches $10,000 from the left. They have to be approaching the same value. So how would I get that to happen? Zach, I can tell you know what you're supposed to do next.
Well, you plug in both numbers, 10,000 to 0.14 and 10,000 to 0.21, right?
Uh-huh.
Because you have to have them match up.
Yes, that's it. What do you have to have match up?
The y value.
All right, so what you want to have match up, I'm going to write down what you said in an equation form. You want to have the second line of this sort of piecewise function match up to the third line of this piecewise function, right? But only at one specific place, only when x is $10,000. So I really only need this to happen when x is 10,000. So I'm going to plug 10,000 in for x, and then notice the only thing that I won't know then is the value for C. And can I find it? Sure I can. So what do you get for C? Do you get a C? Negative 700? Does anybody else have that value? I got some nods. Yeah, it's negative 700. Now, that's not an amount like of taxes. That's not what this number is meaning in the sense of what's going on. But it is the value that will go in the place of the C in order to make the function continuous. Okay? So then if you made $15,000, you'd actually be plugging in your number into the third line of the equation in place of the x. And the negative 700 would affect how your tax rate is actually valued. Okay? Does that make sense? Okay, you're going to do an example like that in your homework too. The last thing in this section is something about the intermediate value theorem. So the intermediate value theorem says the following. Suppose you have a smooth continuous function. You've got one of these continuous things going on. And it's continuous on the closed interval from a to b. And you've got some number between a and b, okay, or between f of a and f of b, let me say it that way. So I could write this in interval notation if you prefer. We're saying that f of a is less than, or, no, we said between, so I'll strictly say less than. F of a is less than, w is less than f of b. So you've got some y value between the two y values. Then there has to be an x value that corresponds to that. And visually, you guys know this is true. I'm going to draw a little quick picture of what's going on here. Let's say right here that we have a graph. Here's A, here's B, and over here somewhere is the f of A and the f of B. Right, so this is f of A, and this is f of B. All this is saying is that if you pick a point somewhere between A and B, over here, there was a point that it corresponded to, and that value, which they're calling C, is actually between the A and the B on the x value. Okay. The only way that could happen is if the graph sort of jumped around, or had holes in it, or asymptotes, right? And it can't. Why? Why can't it have those features? How did it describe the function? Because it said it was continuous. So because this says it's continuous, I can't have any of that sort of, unruly behavior. I can't have any of those things happening between A and B because it was a continuous function between A and B. So it has to follow these sort of nice features of the graph. It has to have this continuity between the values. I've got something weird going on down here, don't I? All right, that should say F. All right, suppose that F is continuous then on A to B, and F of A and F of B have opposite signs. Okay, so one's positive and one's negative. That's what that means, right? They have opposite signs. Then there is at least one number, C, where you actually hit the x-axis. And again, visually, this makes perfect sense to us. If the graph does this, and we have a function value f of A here, and we have B, so here's f of B over here, then there's going to have to be a place where it actually crosses the x-axis. Right? It can't avoid it. This is just a very specific example of the intermediate value theorem is all it is. Very specific example. I want to show you a real life example, and well, I'll talk to you about a real life example after I do this next one about where an intermediate value theorem is actually used, just to give you a little bit of a scare in your soul that this really works in real life. All right, so here's an example first. This one says, use the intermediate value theorem to verify that f of x has a 0 on the given interval. So in order to use the intermediate value theorem, you have to satisfy a few conditions. So the first issue is you have to actually tell me that this is continuous. Why is f of x continuous? There's lots of things we could say. There's one that's really easy, though. Because it's a polynomial is the easiest way to say that. That's right. Very good. F of x is a polynomial, so it has to be continuous. Okay, so if we had something that was not a polynomial, we'd have to argue this a little bit differently. Then the second thing that we have to verify is that we actually have to verify, according to this corollary, that we have one positive and one negative function value on the endpoints. So we test f of 2 and f of 3. What is f of 2? It is negative 3. What is f of 3? Positive 2. Right? I actually have one value that's negative and one value that's positive. There it goes. So because I have this now, so since f of 2 and f of 3 have opposite signs, by the corollary, we know that there's at least one this number, right? There is a C, so between 2 and 3, where f of C equals 0. It's going to have a 0 between there. It's going to cross the x-axis. You can use any of that language. You don't have to use the language I just wrote down. That's what has to happen by that corollary. Now, a variation of this that happens, and this happens in real life, so I know that you guys probably do this too when you drive. You're really a lot more careful about how you're driving if there's a police officer nearby, right? Because they can figure out how fast you're going pretty quickly, right? And if there's no police officer nearby, you might just choose to do something a little bit differently. Well, there are situations where the police are able to figure out your speed, that you're speeding, by not doing what you've expected them to do. That is, they don't actually have to catch you going above the speed limit to know you went above the speed limit. Okay? Because what they can actually do is they can figure out, if they've got 2 police officers there, the distance you've covered and what your average speed would have had to have been. And then they know if your average speed was 67 miles per hour and the speed limit was 60, that at some point you were going at least 67 miles per hour. That's an application of the intermediate value theorem. That's what they're using, and it stands up in court. Right? It's mathematics that's used in real life, and it's all related back to this idea of the intermediate value theorem.